Suppose I am studying a gas. So we might have some box, and we might have a particle, and it's going this way, and we have a particle, and it's going this way. In principle, we're going to have many particles. How many? We're going to have usually on the order of n is equal to 10 to the 23 particles for systems that we're going to be interested in statistical mechanics. So how does one go about describing these systems using physics? Well, if you were to approach this problem from a microscopic perspective, you would describe the system using microstates. So microstates are a description of a physical system that is informationally complete. So what do I mean about informationally complete? What I mean is that if you give me this microstate at some snapshot of time, then I can go about solving the equations of motion, like Newton's law of motion, F is equal to ma, and I can then time evolve the system and tell you everything about its future and everything about its past. In quantum mechanics, instead of classical mechanics, instead I would study the Schrödinger equation, where psi of t is the state and h is the Hamiltonian of your system. So in classical mechanics, we usually take a microstate to be a complete list of all of the positions and momentums of the particles in your system. So if we, for example, had both an x and a y direction, every single particle, you would need to supply its position in the x and y directions, where I will go from the first particle to the nth particle. And we would also need to describe their corresponding momentum. So I'll just write that for convenience in vector format here, p vector I. And this would similarly go from 1 to n. So an important thing to say here is that if we, for example, were to isolate our particles into a box with a volume V, then what we're going to notice here is that the xi's and the yi's are all going to have to be contained in this volume. Now, with that constraint alone, we're going to be looking at an incredibly large range of microstates that our system might be in. And as we go along in this video, we're going to cut down the amount of allowed microstates. But this is an example of a system with an infinite number of microstates. Another example when we study magnetism in classical mechanics is Ising spins. So, for example, we could have a system, and the system would have sort of like slots or lattice sites for magnetic moments or spins. So you could have a spin up, followed by a spin down, and basically every degree of freedom can be up or down. So maybe we do up, up, down, or something like this. But this is an example of a system where it has a finite dimension of microstates. In fact, if we have n spins, then we have 2 to the power of n potential microstates, or ways that the system can configure itself. In quantum mechanics, what we would do is we would describe a complete set of basis vectors. Let's call them psi I. And this would be a basis where you could then take linear combinations of these vectors, and you could construct any other possible vector with those microstates, and this would be our set of microstates that we would work with in statistical mechanics. So basically, any informationally complete set of states or microstates is a valid choice for your set of microstates to proceed and do problems in statistical mechanics, or to describe this many-body problem, whether it's gases, whether it is some quantum system of electrons hopping on a lattice, all you need to do is you need to first describe a complete set of microstates to accurately describe what the system is doing on a microscopic level. But not all sets of microstates are created equally. There is a preferred set of microstates. And those microstates are microstates that allow us to read off the energy very quickly. So for example, in our classical gas scenario, where we just have classical particles moving around and bouncing around, our microstate was an example of phase space, points in phase space. And points in phase space make it very easy to read off the energy. The energy of an individual particle, for example, you're going to get contributions like, let's call this EI for the energy of the ith particle. So you're going to get that particle's mass times that particle's velocity plus a sum over all of the potential interactions with other particles. Right, so we're sum over J such that J does not equal to I. So right away, with our phase space approach to microstates in the classical case, we have a very simple description that allows us to instantly read off of the energy. In quantum mechanics, what we often like to do is we like to work in the energy eigenbasis of the Hamiltonian if that's accessible to us. So we would have the Hamiltonian H, and the energy eigenbasis is defined as the set of eigenkets in the following way. So if I was to just take some energy eigenstate Ek, then I know that its corresponding energy will be this scalar Ek over here. Now the reason why these microstates are going to be more preferable will be obvious right away. So in statistical mechanics, we don't want to work with microstates because this problem is analytically and computationally intractable. You can't make progress working with physical systems in this way. Instead, we want to transport the problem to a problem with macrostates. So macrostates will describe our system in bulk, properties of the system in bulk. So for example, an isolated gas with potentially identical particles can be well described by the number of particles in the gas, the total energy of the gas, and the volume that the gas is contained in. So notice that these three numbers will restrict the type of microstates that will be accessible or allowed by our system. So we will isolate, for example, our system to microstates that only contain n particles. We will isolate ourselves to an energy surface for our particles. So the sum of all of the energies of our particles can only sit at energy E. So that's a surface in energy space. And potentially we might have some type of uncertainty there, but that's a problem for another video. And then of course, our positions of our particles can only sit in a specific volume V. So while for the case of a gas, we're still going to have an infinite number of potential configurations, we have significantly shrunk the amount of microstates that would be allowable. For our Ising spins or our classical spins, we could, for example, also specify a magnetization. So for example, we could have a magnetization equal to 0, which would mean that half of the spins would be up and half of the spins would be down. So previously, when we talked about all of the microstates, we had 2 to the n choices of microstates, but if we then restricted ourselves to a magnetization of 0, what we would find is instead we have n choose n over 2 microstates. Let's round up that 2 a little bit. And what we see here is that this is a significant reduction for our finite dimensional set of microstates. So the number of particles, the energy in the volume, is not the only choice that we could make to describe our system in terms of its macroscopic properties. For example, we could swap out energy for the temperature. But we're going to leave discussing when and why we can do that and the implications of this for a future video. For now, the number of macroscopic variables that describe a system and which macroscopic variables you will choose will very much depend on the system that you are studying. And there is a systemic way for you to isolate which macroscopic variables you need to form a complete set. So a very important thing to reiterate here is that for every macrostate that someone might give you or that you might write down, there will be a significant amount of microstates that belong to that macrostate. So the macrostate sort of washes away all of the microscopic information and leaves you with a description of your system in terms of its macroscopic quantities that could correspond to an incredibly large amount of microstates or potentially an infinite number of microstates. So these are properties of the system in the bulk. And if you had guessed, the reason why we like microstates that you can easily read off of the energy from that microstate is because energy is itself a very important macroscopic quantity that we're going to want to talk about. So now that we know why macroscopic quantities are going to be important, in particular because we want them to be the only thing we need to potentially describe our system so that we don't have to care about the microscopic components in our system, we can then start talking about macroscopic quantities and properties of the system that fall into two categories. One is intensive quantities and another is extensive. So to do an example, we could, for example, think of two containers, okay? This one container will have a volume V1 and it will have a temperature T. And we're going to combine it with another container with a volume 2 and a temperature T. Now, if we wait long enough, these two systems will come into equilibrium with each other, and we will have another system with these two combined with a volume V1 plus V2. And what the temperature is going to be is it's just going to remain T. So intensive quantities are quantities that are independent of system size. And extensive quantities are quantities that are going to be dependent on system size. So the most trivial one of these will be the volume. So energy is also extensive. If I take two containers and I combine them, the energy will grow linearly with the volume of the total system. So we can write energy here. And also, of course, the number of particles. Now, what are some other intensive properties? Well, for example, we could take two extensive quantities, let's say E and N, and we could divide them, getting the energy density per particle. Now, this would be an intensive property. If you've taken some thermodynamics, you would also know that, for example, the chemical potential, which we will discuss later, is also an intensive quantity. You could, for example, also have the particle density, the number of particles divided by the volume. And a special quantity that we are going to talk about in detail over the next several videos is a quantity called the entropy. The entropy is also an extensive quantity. Combining two systems will, in general, grow the entropy linearly with the system size. So let's do a quick summary. We had we had our microstates. Microstates are a microscopic description of your system. It is a state of the system that would allow you to time evolve your system forwards and backwards in time in such a way that you could make physical predictions or whatever about that state. So it's an informationally complete description of your physical system. Now, a macrostate instead will take the most important information about a set of microstates and contain it into a small number of quantities, like the energy, like the number of particles, and like the volume. So there'll be a large number of microstates belonging to one single set of macrostate variables. Macrostate variables or macroscopic quantities will fall into two categories in general. I mean, they don't always have to fall into these things, but those will be intensive properties of the system, which are properties that are independent of the system size, and extensive properties of the system, which will grow linearly with the system size. But that's all for this video. I hope you found it helpful. If you did, feel free to like, subscribe, and leave a comment below.